Hi, this blog post is going to be on running CPM on the RC2014. If you're not familiar with the RC2014, please go back and watch some of my previous videos or visit my website at www.smbaker.com. My first video, Intro to Z80 Retrocomputing, will tell where I bought the RC2014 kit from, and subsequent videos will describe various boards that I designed myself to go along with the kit. This blog post is going to be on running CPM, and we're going to have to introduce a new board for that, but first let's state some of the requirements that we're going to have for CPM. CPM is a disk operating system, so it's going to need a disk, and we're going to use compact flash for that. The previous blog post right before this one discussed the compact flash board. We're going to need a CPU, a clock. The standard RC2014 CPU and clock are sufficient for those two. We're going to need serial I/O. So we use the SIO board, which I demoed a couple blog posts ago, that is different than the 68B50 that comes with the RC2014 kit. The reason I did that is because the blog that I based this implementation off of, Grant Searle's blog, he used the SIO chip. He already had a BIOS written for it. Everything's all pretty much good to go and ready to use with that, whereas it would take some modification to use the 68B50. We're also going to use 64K of RAM and up to 16K of ROM. We probably only need a couple kilobytes of it, but it's easy to switch in the ROM in 16K chunks, so we'll do that. As you're probably aware, the Z80 can only address 64K at once. So what we're going to have to do is we're going to have to bank switch between the 16K and the 64K. And here is a picture of the CPM memory map. So over here, this is going to be a running system. It's going to be all RAM from 0 hex all the way up to FFFF. So all 64K will be RAM. At the top, the high addresses will be the BIOS, the BDOS, the CCP. There's going to be a huge chunk of it is going to be program space to run whatever program you're running in it. And then I think the first 100 hex is going to be the CPM workspace. So that's at the very bottom. Obviously we can't boot into RAM, we need to boot into ROM, so we're going to use a bank switching technique where when the RC2014 boots, the bank switch will have selected a ROM, and then the ROM will be running a monitor program. The monitor program will execute for a while, sort of set up the computer, then it will jump up here into a place in the BIOS, and the BIOS will instruct the bank switch to switch over to RAM, and then we will have this whole RAM set up. So that's the key thing that we need to re-engineer the RC2014 to do, is to do this bank switching so we can switch the lower 16K. This is all the lower 16K between ROM and RAM. The upper 32K will always be RAM. So that is going to require us to build and design a new board. And that board is the banked RAM and ROM board. So I could have used a single 64K RAM chip, but I had plenty of these 32K chips laying around, so I used two 62, 256, 32K RAM chips to make up the 64K of RAM that we're going to use. And then I also used a 27C512 EEPROM to make up the ROM. Now that is, I believe that's a 64K ROM EEPROM chip. We could have gone with a smaller chip, but they all cost about the same on eBay, so I went with a big one. And what we will do is we will only enable 16K of this ROM at a time. And then there's a couple jumpers down here which let you select which 16K window you want out of this ROM. So you could have, you could segment this ROM into 4 pieces and have 4 different bootloaders into it, and then jumper into whichever bootloader you want. And I do that. For example, one of them I run the CPM monitor, the other is basic, and the other's a switcher for my bus supervisor board. So it's nice to be able to run 4 different things in the EEPROM. So here's our 64K RAM on this side, and our 64K with a 16K window EEPROM on this side. So the trick is going to be switching the low part of the address space between these two. There's 16 address lines, A0 through A15. A15 is responsible for selecting the most significant bit of the address, so it'll select between the upper and lower 32K. So what we want is when A15 is high, we want to make sure that the high RAM chip is always selected. When A15 is low, we want to select either the low RAM chip or the EEPROM. And all of that is going to be handled by this flip-flop and decoder circuitry down here. So starting on the left, I have a 3 to 8 decoder. What this does is it selects an address to place the bank switcher at. So the bank switcher is going to be a port. Just like any other port on the Z80, we can write to it. And when we write a number, 0, 1, 2, 3, or 4, it will select between the EEPROM, the lower RAM chip, or any of 2 external RAM chips that we could want to page in. We're not going to actually use those external RAM chips, but pretend we could, and then we could have a 128K computer if we so desired. So this here does the I/O address for bank switch. To maintain consistency with Grant Searle's CPM implementation, I chose to address this 3 to 8 decoder in such a way that I can put it on the same port that he used, which I believe is 38 hex. So for 38 hex, I think you jumper it down here at the highest position jumper for the 3 to 8 decoder. So then we go into this bank switching logic over here. Now there's a couple of flip-flops here that I use to store the current state of the bank switch. And that'll store 2 data bits. That allows us to select any of 4 banks. So the way flip-flops work, of course, is you can clock it, and it will clock that data into the flip-flop. And the handy thing about a flip-flop, at least this type, is it also has this reset clear bit. And if you put this clear bit low, then it'll reset the flip-flop to zeros. And we're going to use that to handle our power on situation. So when we reset the computer, we always want the EEPROM to run, because the RAM will either be empty or it'll just have random junk in it. So we want the EEPROM to run. Resetting clears the 2 flip-flops. We'll set it to 0 and 0. Otherwise, we can write whatever we want into it and set it to different value. And then over here is a 2 to 4 decoder. So the output of the flip-flops will form the selection of which output to drive on the 2 to 4 decoder. And then our A15 also comes down here and enables the 2 to 4 decoder. So when A15 is low, this decoder will be enabled, and if these 2 bits going into it are 0, 0, then it will make this ROM CS first output here low, which will enable our EEPROM. When A15 is low, if these are 0 and 1. Then it will make RAM low chip select low, which will enable that RAM chip. And then the other two I just ran out to a header in case you want to run some external RAM chips off the bank switching logic. The boot up logic is this. So you hit reset. Reset puts 0 in the flip-flop, which causes the EEPROM to be selected. The EEPROM runs the bootloader. The bootloader causes some stuff to be loaded into RAM. Then the bootloader is going to jump to the RAM program. The RAM program is then going to write a 1 to the I/O port that's associated with this jumper. That 1 will be stored in here in these two flip-flops, and that 1 will cause RAM low CS to be selected instead of the EEPROM CS. And that is our bank switching logic. If we ever wanted to switch it back again, we could just write a 0 to this port, and that would set this flip-flop to 0, and the EEPROM would be selected. Presumably there's no reason why we would want to, on a running system, bank switch back to the EEPROM, but we could do it if you had some need to do it. Similarly, you could also write a 2 or a 3, and it would enable whatever RAM chips are connected to this external header. Now down here on this last chunk of the 2 to 4 decoder, what I needed was an inverter so that when A15 is high, it would enable the high RAM chip. So I just wired this half of the 2 to 4 decoder as an inverter so that I wouldn't have to add another chip. Okay, so here's the board that implements the dual RAM and ROM bank switching. So we have two RAM chips. They're the 62, 256, 32K each. That's this chip and this chip. We have the 27C512 EEPROM. I put a piece of black tape over the window so it doesn't get inadvertently erased. These two jumpers allow you to select which 16K window of the EEPROM you want to use, so we can load up to 4 different bootloaders in the EEPROM and select between them with jumpers. Over here we have our 3 to 8 decoder. This header selects which address on the 3 to 8 decoder that is used, and the address that I have enabled is 38 hex. Here's the 74HCT139, that's the 2 to 4 decoder that drives the chip selects. Over here is the 74HCT74, which is the flip-flops. And then this one is an OR gate, which is used to generate the memory read and memory write lines for the chips by combining the Z80's mem request with the Z80's read and write. I didn't go over that on the schematic. It seemed simple enough. Okay, to implement, to get CPM running, we're going to use 2 more boards that I've covered in previous posts. That is the compact flash board. I'm not going to describe these 2 other boards in this post because they've already been described, but you'll need the compact flash board for storage, and you'll need the SIO board for serial I/O. The SIO has two different serial ports on it. You only need to use one of them, and the way I've set it up, you just plug an FTDI header into it. This one I have jumpered to address 80 hex, and then the compact flash I believe I had jumpered to address E0 hex. So we will install those in our RC2014 and okay, I'm going to attempt to demo a fresh installation. I've only done this once before, so let's hope I remember all the steps. First step is going to be to insert a fresh compact flash card. I have a 64 megabyte Cisco card that I got off of eBay. Plug that in while the power is off. Then I will power up the RC2014. Press the reset button. So we have the spacebar prompt, and that is to let the monitor software in the ROM know which serial port we're on. It outputs that to both of them, and then we push a space on one of them, and then it knows which one we're using. So there we have it. We're in the monitor. Okay, there's going to be 3 phases to this. So the first phase is going to be to format the compact flash card. So over here I have another tab open that has, now these, I patched these programs slightly because I'm working with different addresses than Grant Searle used in his computer. So I've relocated some stuff that was at 4100 hex to 8100 hex. I'm using the compact flash at address E0, whereas he had it at 00. So you'll notice some of the addresses and commands that I will do in my demo will differ from what's on his blog post. So use that accordingly. You know, if you're using my boards and you've configured them the same way, then these addresses will be right. So let's look at the, we want form64.hex. So we will take that. We will copy it, we will paste it, and then G8100. That's because I've relocated the format tool to 8100 hex. And then we will run it. So it has formatted drives A through H on that compact flash card. Now the next thing we're going to do is install CPM on the appropriate sector. So we're going to need CPM 22, let's copy this, it's a long one, so we'll paste CPM 22.hex, then we're going to need to paste a cBIOS. Here, let me get cBIOS 64.hex. Copy that one and paste it. And then we need put sys.hex. Right. Then as with the others, I've relocated that to 8100 hex, and I will execute. Executing put sys will copy the BIOS and the CPM that we just loaded into memory. It'll copy them to the flash drive. System transfer complete. Well, that was very quick. So what we can do now is we can reboot. Here we are back in the monitor. The monitor has several commands. If we do X, boot CPM, yes. And there, we're running CPM. So we do a dir, there's no files in CPM. That's because we haven't actually installed anything. So what we're going to do now is we're going to reboot again. We're back in the monitor. We're going to cat down 8100.hex. Copy that, paste it here, then we're going to FFE8. So this is jumping to a special address in the BIOS. That what it will do is it will relocate that stuff that we just pasted down to 100 hex, which is the running program area in CPM, and then it will load CPM. So we're running CPM, but now this time we're running CPM and we have the download.com program is sitting in there at 100 hex, and we can just type save to download.com. So now if we do a dir, there's a download.com. So now that we have download.com installed, we can actually use it to download our first programs into the system. So Grant Searle has on his website a list of some sample utilities. I've already downloaded these. Transient apps package. So they're in a big file that you can cut and paste. I will only, let me do that again. I will pick one of the smaller ones that's in here. Let's do stat.com. So you can see this starts by running the download program, stat.com, and then it just we're going to just paste this stuff into it. Okay, let's paste it and see what happens. Okay, so the reason that didn't work is because there's something wrong with flow control in the way that I have my RC2014 set up. I don't know if it's the FTDI cable, or it's the drivers on my Windows box, or it's the terminal program. But for whatever reason, flow control doesn't work. It's very easy to overflow the serial buffers. So what I will do is I will add, I don't know, let's just try a 1 millisecond delay between characters. We'll go back in, boot CPM. We still have this stuff in the copy-paste buffer. And then we will paste it again, this time with a delay between characters. It's going to take a while, just because we've added that artificial delay. Okay, so we finally finished. It set the whole thing. An OK indicated the checksum was good. Now if we look, we've now got a couple programs. We've got download.com and we've got stat.com. So if we run stat, it can tell us that the A drive has about 8 megabytes of free space. We can stat download.com. It can tell us some stuff about download.com, 4 records, 4K, etc. We can stat the stat command itself. What? Spelled it wrong. Stat.com. 41 records. So, you know, that's a basic CPM system. So you would paste in the rest of Grant Searle's set of sample programs, and then you would get various things like a line editor, stuff like that. So there's like half a dozen or so things that makes the CPM system a little bit more useful. Okay, let me swap in the compact flash card I have that already has some programs running on it, so we can see a slightly more developed CPM system. Plug in, reboot, space, X, Y. So here I have a lot more software. We can see download.com is there, but I also added, where is it, Xmodem. Xmodem is something that, you know, I used back in the day with bulletin board systems. It's very easy to use Xmodem to upload something with the terminal program, since Xmodem's already built into the terminal. So that was the first thing I did, was get Xmodem running. There's also a bunch of other tools, so like we could dump xmodem.com, and it'll hex dump it all out to the screen. mbasic is Microsoft Basic. Print hello world 20 go 10. Standard Basic. I don't know if there's a way to exit it. We can just reboot. What else did I install? I installed Zork 1. It's the good old Zork game. Your small mailbox here. Open mailbox. Take leaflet. Read leaflet. South. Look. I mean, your standard text adventure game. Can I exit? Can I quit? Do you wish to leave the game? Yes. I also installed Turbo Pascal. So we can run Turbo, include error messages. I was a Turbo Pascal programmer back in the Windows and DOS computer days, so Turbo Pascal is convenient. It actually has an editor. Oh, I've already written a Pascal program. What do you know? Oops, and I just erased it. See, that's me. I don't know how to use it. Let's try that again. So let's try that again. Let's try that again. X, Y, turbo, foo.pass. Foo.pass. So, you know, it's got an editor. I don't remember how to actually... It says, let's see, Control K D will leave the editor. Yep. What can we do? So let's compile foo.pass. And then can we run it? Yeah, we can run it. Hello world, and then it's waiting for keystroke. Good enough. So that's you know, I did a lot of Turbo Pascal back in the day. I don't think I have anything else super interesting on here. There's an assembler. You'd have to give it a source file and it could assemble for you. But there's lots of resources out on the internet. You can find various programs and such to install in your CPM computer. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.